So good evening, everyone. Let us start today's discussion. It will be the last discussion for this course. So let us start then. So we will basically be focusing on the design on what we till the last class we have tried to learn the design of various structural elements, say beam, column, slab, footing, okay, staircases. So in this lecture basically we will be basically summarizing and trying to apply those concepts in the design of a multi-story building frame, because what we learned till so far was uh, like how to design a particular specific or individual section, right? But now we will see as a whole how to approach design of a multi-story building frame. Okay, so for this purpose we will be basically considering a G+3 building, okay, that is a 4-story building, okay. And because it is not possible to calculate manually at each and every section or point, so we will basically taking the help of a software, okay. So any software, structural analysis software, you can take help of, such as SAP 2000, ETABS, StatPro, etc. Okay, so yeah, so let us see. So yeah, so that is what it's all about. So this is the overview of the presentation. First is design of RC elements, second is design of the G+3 story school building, then plane frame analysis, design of beams, summary, and IS codes required. Okay? So yeah, so what we all know is any structure, okay, if any stresses are applied, okay, so it can be categorized into 4 parts. One is axial force, one is flexure, one is shear, and one is torsion. Okay, we can also say that flexure shear is almost like it was we can say, like, we can quote one and the other will be always be there, okay, because shear will create flexure and flexure will create shear, okay. So basically there are three: axial force, flexure, shear, and torsion, okay, but you can separate it also, no issue. So yeah, so as I told you, we actually discussed the design philosophies in the previous classes for all these types of structural elements, that is singly reinforced beam, doubly reinforced, flange section, shear, okay, beams, and we understood how to design slabs, both one way, two way, columns, short and long, footings, and staircases, right? So yeah, so also last class we understood how to design for torsion as well as deflection, okay, and check it, right? So yeah, so the thing is, as I told you, it is not, although we learned it how to design at an individual point, it is not clear how to apply these design philosophies for a full structure, okay. So it is somewhat like our knowledge is not complete, okay. So we know the parts, but we have to integrate it completely to understand how those philosophies are applied at a building, okay. So therefore we will take an example of a frame structure, okay. So that is, we will take a G+3 storage school building, okay. So we'll take this example and try to understand, okay. So the problem is the plan of a G+3 school building is shown in figure 1 and 2. So this is the plan, okay, and this is a RCC frame structure, and the two-dimensional frame at C is shown in figure 4. So this is this one. So like this section they are showing, okay. And so for this we have to design slabs, beams, and columns of the building, okay. So as I showed you, this is the building plan, okay. This is the elevation, okay, and this is the elevation at grid line C, okay. So like they have designed it in the they have defined and designed and evaluate analyzed in a software, as I told you. You can take any software like SAP 2000, ETABS, StatPro, etc. So yeah, so these are the footings of the school building, okay, and this is the basically the structural skeleton, okay, where they have shown various diamond 3D views, okay. So this is the view 1, view 2, view 3, view, and so the three views they have shown with slab, okay, and without slab they have shown the naked skeleton, okay. So this is the skeleton, okay, the structural skeleton, various views. So yeah, and if we remove the beams, okay, at one side, okay, so we can also see the planar frames. So these are the frames basically which will be acting, okay, which will be present. and these are the various views of it. Okay, so for this we will be needing some basic data. Okay, so we will assume some basic data, and for design we have to follow three codes basically. Okay, so IS 456 is basically for the reinforced concrete design. Okay, IS 875 is used basically to find out the loads acting. Okay, and IS 1893 is basically for the earthquake design. Okay, so in India especially we have to design every building for earthquake also. Okay, so for that we have to follow IS 1893. Okay, basically the part one. Okay, that is related to your normal buildings. Okay, so these are the IS codes we have to follow: 875, 456, and 1893. And let us assume that the concrete is of grade M25, steel is of grade Fe415. Okay, the external brick walls shall be 250 thickness, and the internal walls shall be 125 Okay, so and the width of the stairs also let us assume to be 1250 millimeter minimum. So these are some of the basic datas. Also, let us assume that earthquake zone is intermediate. Okay, so let us consider third zone, zone 3 earthquake zone. Okay, and yeah, so from the IS 875, so let us assume that the live load acting on the floor is 3 kilonewton per meter square. Live load acting on corridor and staircases will be 4 kilonewton per meter square, because more people will be moving. Okay, and live load on roof is 3. So actually this is not correct. Okay, so in roof it should always be less. Okay, it will be less because there will be no one. Okay, but for uniformity, okay, for easy understanding, they have assumed both as 3. Okay, and let us assume that the plinth level, okay, the plinth, the surface of the base, the ground, okay, or the base floor. So let us say it is at 600 millimeter above the ground level. Okay, so the plinth level is 600 okay, above, and the depth of the foundation, okay, so it is at least 1200 or 1.2 meter below ground level, and the safe bearing capacity of the soil is, let us assume, 150 kilonewton per meter square. Okay, so these are the data we have taken. Okay, and let us assume few more structural data. Okay, data of elements, structural elements. So let us assume the thickness of slab is 125 millimeter, thickness of floor finish is 30 thickness of ceiling plaster is 6 unit weight of concrete is 25 kilonewton per meter cube, unit weight of floor finish is 24 kilonewton per meter cube, unit weight of plastering is 24 kilonewton per meter cube. The dimension of external columns is 300 by 500 millimeter. The dimension of internal columns is 300 by 500 millimeter. The dimension of beams in rooms 300 by 500. Dimension of beams in corridor. So basically everything they have assumed to be 300 500 Okay, but generally it is not the case. Okay, so generally beam dimension is lesser than the column. Okay, so they have follow up philosophy called strong column weak beam. Okay, so that is mainly for earthquake design, so that should be the case. Okay, but they have, for uniformity, they have assumed every dimension to be same. And the dimension of cross beams, so cross beams are basically the beams which are acting at the roof. Okay, so they share the load taken by the roof. Okay, so these are beams which connect the main beams, primary beams. Okay, and in the transverse way at the roof. Okay, so these are the dimension of cross beams, so they have taken it to be 300 by 350 You can say it to be a secondary beam also. Okay, so it is 300 by 350. And so yeah, so that is the assumed data of the structural elements. Okay, and this was the data, basic data. Okay, so yeah, so let us calculate the dead loads. So for slab, the dead load acting will be 0.125 into 25, that is 3.125 kilonewton per meter square. The dead load for the floor finish will be 0.03 into 24, that is 0.72 kilonewton per meter square. The dead load due to ceiling plaster of 6 will be 0.006 into 24, that is 0.144 kilonewton per meter square. So the dead load total slab of the total dead load of slab, floor finish and ceiling plaster per square meter will be 3.125 plus 0.720 plus 0.144, that is 3.989 kilonewton per meter square. Okay, and the dead load due to the brick wall, okay, the outer brick wall basically 250 thick, it will be basically 0.25 into 3.5 minus 0.5 into 20. Okay, so this is because they have assumed each length of each bay as 3.5 meter. Okay, and because the dimension of your this the dimension of your column is 500. Okay, so you have to subtract half dimension of column from each column. Okay, So that is 0.25, yeah, 0.25 from one side and 0.25 from other side. Okay, because that load will be carried by the column itself. Okay, so you subtracting that, minus 0.25 minus 0.25, that is minus 0.5. Okay, so that is 3.5 minus 0.5, that is the length. Okay, and unit weight of brick is how much? They have assumed to be 20. Okay? It is around this. So yeah, so we get this value as the dead load as 15 kilonewton per meter. Okay, and similar case for the internal bricks. Okay, brick wall. So it is having a thickness of 125 mm. So the dead load will be 0.125 into 3.5 minus zero point 0.5 into 20, which is 7.5 kilonewton per meter. Okay, so yeah, so as I told you, we have assumed, okay, that the length of each bay is 3.5 meter. Okay, and we also assume that the slab is cast monolithically, means the slab is cast together with that of beam. Okay, we can separate both. Okay, so it is called monolithic. Okay, so UDL, that uniformly distributed load per meter length of beam due to slab, floor finish and ceiling plaster. So it will be 3.989 into 3.5, that is 13.961 kilonewton per meter. Okay, UDL per meter length of beam due to self weight of beam. Okay, so it will be zero point 0.3 into zero point 0.5 minus 0.125 into 25, that is 2.812 kilonewton per meter. UDL per meter length of beam due to slab, floor finish, ceiling plaster, internal brick wall and self weight of beam, that is 13.961 plus 7.5 plus 2.812, that is 24.274 kilonewton per meter. Okay, and the UDL per meter length of beam due to slab, floor finish, ceiling plaster and self weight of beam is 13.961 plus 2.182 812 equal to 16.774 kilonewton per meter. So basically these are the dead loads we have calculated. Okay, now let us calculate the live loads that will be acting. So length of each bay, as I told, as we discussed, is 3.5 meter. So UDL per meter length of beam due to live load is in room is, we assume this is 3, right? So 3 kilonewton per meter square into 3.5, so it is 10.5 kilonewton per meter. Okay, and UDL per meter length of beam due to live load in corridor, that will be 4 into 3.5, similarly that is equal to 14 kilonewton per meter. Okay, and the loads in different floors that is acting. Okay, so dead load of roof, that will be basically equal to 2 into 24.274 into 7 plus 16.774 into 3.5. So this, if you have seen the building plan. Okay, so this is basically the middle length, middle bay, and these are the n bays. Okay, so there are basically three bays. Okay, in at one direction. So the n ones are basically of the classroom. Okay, and this is basically the corridor. Okay, so these are the loads, and that's why they have multiplied with 2, because there are 2 on each side. Okay, and the base of 7 meter. Okay, at the both ends, and in between it is 3.5. Basically it is having 2 bays. At one classroom is having 2 bays. Okay, so that's why total is 3.5 plus 3.5 plus 3.5 plus 3.4, that is 14. Okay, so that's why 2. So they have found this to be 398.545 kilonewton. Okay, and similarly, if you see the live load of roof, it's the same concept. So this is the load acting per meter length. So it will be equal to 2 into 10.5 into 7 plus 14 into 3.5. So it will be 196 kilonewton. Okay. So similarly, if you see similarly for the various floors, so the load will be same basically, because we have assumed everything to be uniform. Okay, so here note is also mentioned. So both depth and live load of roof will be actually different, okay, from other floors. But for simplicity, the same load is considered. That's why we are getting the same loads, as I told you in the initially also, okay, just before the design. So yeah, so basically if we summarize, so these are the various dead loads and live loads that is acting, and this is the total load. Okay, so this will definitely not be the same. Okay, for roof and other floors, but for uniformity we have taken it same. Okay, so yeah, so that is basically, this is the total load. Okay, so 594.545 into 4. Okay, so that comes around 2378. Okay, 0.1. So basically, here we will be calculating the base shear. So we will be first, like we will be also considering the earthquake design, yeah, earthquake related design. Okay, so for this we have to follow the IS 1893 code. So everything which is done here, so that is as per the IS 1893. You can go through that code. It is a very small code. Okay, so that will clear your any doubts. Okay, that may arise here. So basically we required a zone. Okay, earthquake zone. Okay, so this method is basically called the seismic coefficient method. Okay, seismic coefficient method, or it is also called the linear static analysis. Okay, so for more, you can also refer to this course of earthquake design. Okay, so it will be a separate course beyond the scope of this course. Okay. So for this, we have to assume the earthquake zone. Let us assume the earthquake zone is 3, as we discussed in the assumed data. And for 3, the earthquake zone, okay. So the Z value, zone factor value, this value, that is equal to 0.16. Okay. And yeah, so let us assume the importance factor is 1. Okay, so this I value will be 1. Moment resisting factor, frame factor equal to 5. So this R value will be 5. Height of the building H is 14.6 meters, so they have total it, okay, for the 4 stories. And width of building D they have assumed as 17.5 meter, okay. And so for using these values we can calculate the time period, okay, which is equal to 0.09 h by square root d. So this formula also is present in IS 1893, you can check that. So that is the time period. So putting the values, we get the time period as 0.314 second of the building. Okay. So based on this, we can calculate the SA by G value as per IS 1893. So that comes out to be 2.5. Okay. So this SA by G value will be 2.5. So based on this, we can calculate the alpha H value because we know Z, I, R and SA by G. Okay. So putting these values, we get alpha H value to be equal to Z by 2 into I by R into SA by G, which is 0.040. Okay. So as per again the equivalence, this one, seismic coefficient method. So it will be your this one, the base shear. Okay. So base shear will be equal to VB, okay, which is equal to alpha H into W. Okay, so W is the total load acting on the building, that is all sum of all those all 4. Okay, and your this the alpha H value is zero point 0.4. Okay, so we have to multiply both. Okay, so multiplying both we get the base shear. Okay, so that is the lateral force that will be acting. So that will be equal to 0.04 into 2378.18, which is equal to 95.127 kilonewton. So that is the total lateral force or shear force that is acting in the complete building. Okay. So if we want to find, okay, that how much shear is acting at each story or each floor, okay, so we can calculate that also using that equivalent static method. Okay, so for that you can refer to IS 1893. So that will be basically equal to this formula WIHY square by summation WIHY square into your this VB. Okay, so if you total this, like that is the QI value. If you total this, it will come to be 95.127. Okay. So how to do this? You can refer IS 1893. Okay. So they have calculated WI, they have calculated HI. Okay, and this is the WIHY square values and summation. They have found the WHI square by summation WHI square for all the levels, and then they have multiplied this with this value VB value, and they have found the QI. Okay, so this is the QI values. So as predicted, the roof will have the maximum shear lateral force, okay, because it is at the top, right? And the base will have the minimum. Okay, so base story, like the base story will have the minimum, and summation will give you the total. Okay, but the reaction, the resisting thing is the opposite. So this is the acting. Okay, acting thing is the maximum at top, but resisting thing is the maximum at bottom, because the foundation is at the bottom, right? So this is having the minimum shear force acting, but this will have the this floor is having the minimum shear force acting, but this floor will also have the maximum resisting shear force. Okay? So yeah, so these are the values we have calculated for inputting in the software. Okay, so we will input these values in the software, and we will take various load combinations. Okay, so as we discussed in the first class or second class, so various loading configurations combinations we can give. Okay, like dead load with respect to dead load, live load and earthquake load. So these are the various combinations. Okay, so they have considered 10 basically. So yeah, so using this, let us perform the plane frame analysis. Okay, so for this we'll be using the software as I told you. So after analyzing, so we'll be analyzing in the structure analysis software from say SAP 2000, ETAPS and STEP Pro, etc. So giving all this data, okay, and analyzing, so we'll get these results. We'll be getting generating these results, okay. So these results will be generated in PDF. So these are the values, okay. So they will assign each node, okay, to each point of the building, okay. So basically they follow, this follows the finite element analysis, okay. So if you're interested in how it is, it is assigned nodes and elements, so you can also study that course, okay. You can take that course in future, so that will be helpful, okay. So based on this analysis, they find these forces, okay, reactions basically. So Fx, Fy, and Mz. Okay. So M is basically the moment in the Z direction. So these are the values that have been generated. Okay. So for the reactions basically, and if I say you that our main purpose of analyzing in software is basically to find the forces only. Okay. Because if we know the forces, we can design. Okay. But it is not possible to manually calculate at each point. Okay. We know we need the critical value, okay, the maximum value. Then we can design the elements based on that, okay. So for that we take the help of software, okay. So these are the results basically, and these are the values, okay. These are the values they have calculated based on our sectional dimensions that we have given element data. So these are the results, okay. And if we look here, so yeah, so they also give the displacement values, okay. So because it is the ground floor, there is no displacement, okay, because the base is will be moving together, so there is no relative displacement, okay. So that is 0, okay. But if you go in the first and higher stories, it will have displacements either in positive or negative direction based on the various load conditions, okay? So they have taken the first three cases basically, okay? So that is because of there is one I forgot the term. So you have to you have to see the shape, okay, the mode shape, okay. So mode, there's a term called mode participation factor, okay? So you have to find the like it is stated, the mode, all those modes participation factors whose summation gives man more than 90% contribution, okay. So only those mode shapes are considered, and basically first two or three contributes to the maximum, like more than 90% of the mode participation factor, okay, contribution. So that's why they have taken that first three only, okay. So for more this one more understanding, you can opt for the earthquake analysis and finite element analysis courses, okay. So based on this, they have generated these displacements, okay. This is the xy and this is a theta rotation, okay. So always remember reaction when in case of finite element, when we talk about reaction, okay. So reaction does not mean only force, okay, it also means moment, okay. So f means force, m means moment, but all are reactions, okay. Yeah, that may be, like I had problem initially to understand like how moment is a reaction, but that is also considered a reaction only, okay. And it's similarly in case of displacement. So displacement does not mean only deflection, okay, it can also mean rotation also in case of finite element. So always be clear with that, okay. This is not delta, it is theta, okay, but these are delta, okay. So all are coin displacement, okay. You have to check the unit for finding what is it is deflection or it is rotation, okay? So these are the values which have been generated for each floors, and the higher you go, more will be the value, okay? So yeah, so these are the values which have been generated, and yeah, they have noted given note that ground floor, it is because ground floor it is fixed, so it will definitely have no displacement and no rotation, because if it moves, the soil will, the ground will also move, so that means it is not having any relative value, okay? So that means it is 0. So yeah, so these are the values for columns which have been acting. Initially I think it was for beams, now it is columns. So at various locations, say left intermediate, okay, right intermediates. So these are the results, okay, based on the analysis of the structure using a structural analysis software, okay. So they have generated these results, so you have to study this, okay, and you have to find a critical section basically, okay? That is the section having the maximum, okay, so that you cannot design for each and every point and this one, okay, note, okay. So that is not required also. Best thing is to do is to take the maximum value, okay, and that is like that will give the maximum factor of safety, and take into consideration the critical maximum value and design everything based on that only. In, if you remember in the earlier classes, okay, So what we while we solved the problems, what was given was the value, the mu value. Okay, so that mu value is found using this structural analysis. Okay, so like using this software, if you get that mu value, you can design everything. But for designing, we need that mu value. So mu or f value. Okay, so for that only we are running this analysis for the entire building. Okay, so one value you get the critical, you can design for the whole building. Okay, so now let us see how to design the beams, okay, based on this value. So they have assumed that they have found that basically that element number 17, okay, so that is having maybe the critical value, okay, that is having the critical value because it is in the first floor. Okay? So basically the load will be, as you go down, the load will be more, right? More the roof will be having, say if roof is having 500, then third floor will be having more than 500, okay, because it will be 500 plus something. Okay, then second floor will be 500 plus something, then first floor will be 500 plus something plus something plus something, right? And ground floor will be having the maximum. Okay, but ground floor will be distributing everything to the ground. Okay, so it will actually not be having any load. Okay, so that means the maximum load will be carried by the first floor. Okay, the floor just above the ground floor. So they have found that element number 17 is having the maximum or the critical moment. Okay, maximum moment. Okay? So maximum moment due to dead load or and maximum moment due to live load. Okay, so based on this, let us design. Okay, so therefore the design moment we have to consider is 1.5 into 57.995 plus 1.5 into 24.797. Okay, so, sorry, so that means it will come, the value will come to be around 124.189 kilonewton meter. Okay, so based on this we have to design. Okay, so let us consider these are the consideration we have to take. That is beam concrete, the characteristic strength FCK is 25, Fy 415. We have assumed this. Mu value is 124.189. We just found this. B let us take as 300. Overall capital D as 400. Okay, and clear cover CCS 25 mm. Okay, and yeah, so effective depth D. Okay, capital D. If we know this, we can find the effective depth capital ds, sorry, small ds, capital D minus cc minus phi t by 2. So we have also assumed the reinforcement bar diameter is 16 mm. Okay, so therefore effective depth will be 400 minus 25 minus 16 by 2, which is 367 millimeter. Okay, yeah, so one more thing, when we analyze the structure. Okay, so we actually give some dimension of beam, if I remember. Okay, I think it was 300 into 500 or something, right? So that was required for just an estimation. Okay, so that means like we just have to give a standard value. Okay, so that is generally standard value for getting this value. Okay, and based on this value we can actually design. Okay? So that was not the actual design, that was just an assumed value. Okay, now we will be actually designing based on the moment we have generated. Okay? And definitely that value will be similar. That was, I think, 300 by 500, this close 300 by 400. Okay? But if we give 300 by 500, that is uneconomical. Say for example, if it is satisfying here only, why to give that value? Okay, and you are not like, we are not only casting one beam, we will be casting a number, hundreds of beams. Okay, because it will be a G plus 3. Okay, so therefore it will be a huge uneconomical section if we give unnecessary dimensions. So yeah, so taking this dimension, so let us see. So the coefficient QUB, so that is basically that 0.36 into your XU by D, okay, into 1 minus 0.42 XU by D. So this we have already designed in beams. Okay, so putting these values, okay, so they have taken limiting condition. Okay, so that's why, that is why 0.48. So QUB coefficient comes to be 0.138. Okay, and that is using that we can calculate the moment of resistance, which was 0.13 FCK BD square, right? So putting the values, we get the moment of resistance to be 139.185 kilonewton meter. Okay, which is more than 124. You see, so that means this is sufficient. Okay, so we don't have to give here 500 or 467. That will be much higher. Okay, so that's why it's important to design again. Okay, so this is real, so this is sufficient. Okay, and lever arm factor J can be calculated using this formula. Okay, so putting the values, we get the lever arm factor J is 0.830. Okay, so based on this we can calculate the area of tensile reinforcement, which is mu by 0.85 0.87 fy Z. Okay, Z is nothing but JD. Okay, so yeah, so yeah, so uh, yeah, so putting the values, basically we get the area of tensile reinforcement ASTR as 1129.6 mm square. Okay, and that is the required value. Okay, so assuming that we have provided for 16 mm diameters and providing 16 mm bars, 6 numbers. Okay, so our area of tensile reinforcement provided will be 1206.4, which is higher than 1129. So that means this is okay, right? And you can get this for formulas by referring to annexure G. Okay, so annexure G of IS 456 you can refer to for getting all these values formulas. Okay, so from there only moment of resistance due to steel. Okay, so that is 0.87 Fy AST into 1 minus Fy AST by 0 FCK BD into D. Okay, so putting these values we get the MUSP, or the moment of resistance due to steel provided. Okay, so that is 130.776 kilonewton meter. Okay, so from concrete also it is higher than 124. Okay, and from steel also it is higher than 124. So that means it is the section is okay from both tensile as well as in compression. Okay, and because this is 130 is less than 139, we can also say that it is an under reinforced section, which ideally it should be. Okay, so from that angle also it is safe. Okay, so like this we have to design. Okay, so this they have shown the design for beam. Similarly you can design for column, which we have done. Okay, you can design for slabs, you can design for footing, you can design for staircases, and you can also check for deflection and torsion and all other limit states. Okay, so this was just an exemplary demonstration, example demonstration on how to solve. So if you know basically the moment value, okay, critical moment value, so this is the critical moment value. Okay, because it is the maximum. Okay, so taking this you can go for everything, you can go design for anything. Okay, so similarly if you need force, you can find a critical force, it will be also in the first floor itself. Okay, so like this you have to go for the design. Okay, so this was just an example. Okay, so our demonstration. Okay, simple demonstration. So basically if I summarize, so this example is only taken for a demonstration. For more detailed analysis, it can be carried out considering different roof load, so that will be a accurate one. Okay, here for uniformity, for simplicity, we have taken uniform values, but actually the roof load will be much lesser. Okay, and because no one will be there, right? No load will be there, like live load. Okay, or even dead load, so it will be less. And load of transverse, in this case load of transverse walls were not considered because they were not structural specimens, right? So that's why they were not considered in calculation of lateral load due to earthquake, but ideally they have to be considered. Okay, if you talk about large like high rise buildings, you need to consider. Okay, because it will be too high to neglect. And it is possible to solve the problem using commercial software, just as I mentioned. You can use SAP 2000, ETABS, STEP Pro, etc. Okay, and an attempt is made here to show the calculation at different stages, so they have just given a demonstration. Okay, so it is a very exemplary demonstration to understand how to design. Okay, and as I told you, these are the IS codes. Okay, you have to consider basically 456 2000. It is the bible, okay, for a reinforced concrete design. And IS 875, it is as per your it is from 1987. It is little old, but it is still used for taking the loads. Okay, for designing as per loads other than earthquake. For earthquake you have to refer to one is IS 1893, part 1 for the residential and commercial buildings. So yeah, apart from that, dead load, live load you will get from IS 875. Okay, part 1 to 5. So 1 is for dead load, 2 is for live load, 3 is for wind load, for I think I forgot actual, like I think it is for snow or some ice load, something like that. And 5 is for various combinations. Okay, so those loads you will get there, but basically we are mainly required a dead load, live load, and earthquake. Okay, dead load and live load you are getting from 875, earthquake you are getting from IS 1893 part 1. Okay, so here it has been mentioned 2002, but a latest version that they have, like we consider the latest version as 2016. Okay, so you can, instead of 2002 you can consider 2016, but almost both the codes are similar. Okay, few things are different, so that is not of our uh, that much concern. Okay, so it will be giving same values. Okay? So yeah, so with this we come to the end of the lecture part. So let us now solve the go through the solve problems and try to better understand. Okay, so first question: as per IS 1893 Part 1 2002, zone factor for seismic zone 2 is A 0.1, B 0.24, C 0.3 or D 0.36. Okay. So there are four zones, okay, 2, 3, 4, and 5, okay, and they have zone factors of zero point 0.1, 0.24, zero point 0.3, and 0.36 respectively. Okay. So zone 2 is basically zero point 0.1. Okay. So you can see here also. So as per table 3 of IS 1893 part 1 2. So I have mistakenly given like provided the latest version, but you can also go to the 2002. It is same. Okay. So the zone factor for seismic zone 2 is zero point 0.1. Okay. So A 0.1 will be the correct answer. Okay. Second question: base dimension. Uh, base dimension of a reinforced concrete frame building with brick infill along lateral direction is 12 meter. Okay. As per IS 1893 Part 1 2002, fundamental natural time period of vibration of the building of height 30 meter would be approximately as A 0.026 second, B 0.354 second, C 0.538 second, or D 0.779 second, which is the correct option: A, B, C, or D. So we basically need to find the fundamental natural time period of the vibration of the building. Okay, so if you remember, that is equal to, just we discussed in the discussion just a few slides away. So this T value is equal to 0.09 h by square root D. Okay, so here h value is height. Okay, that is 30 meter. D value is 12 meter. Okay, because along lateral direction dimension is 12, so it will be 0.09 into 30 by square root of 12. Okay, that will be the fundamental natural time period. So as you can see here, so as per IS clause 7.6.2 C of IS 1893 part 1 2007. So here also I have mistakenly given the latest version, but you can also refer to 2002. It is almost this. It is the same. Okay. So the approximately fundamental natural time period of vibration of RCC frame building with brick infill would be calculated as T equal to 0.09 h by square root D, which is equal to 0.09 into 30 by square root 12, which is equal to 0.779 second. Okay. So that means D 0.779 second is the correct option. Okay. Third question: if the second floor, say, of a RCC building is subjected to imposed load of 5 kN per meter square, as per IS 1893 Part 1 2002, the magnitude of imposed load of that floor that need to be considered in seismic weight calculation of the building is A 4.5 kN per meter, B 2.5 kN per meter square, C 5.0 kN per meter square, or D 5.5 kilonewton per meter square. Okay, so how much we need to consider? Okay, so if the building is subjected to 5 kilonewton per meter square imposed load. Okay, so how much percentage we have to consider of that imposed load? Okay, for the seismic weight calculation of the building. Okay, will it be 100%, that is 5? Will it be 50%, that is 2.5? Okay, will it be 90%, that is 4.5? Or will it be more? Okay, 110%. Okay, that is 5.5. Okay, so let us see. So if you see, refer to IS as per table 10 of IS 1893 Part 1 2016. So again, I have mistakenly provided from 2016, but it is also same. Okay, you can refer to 2002 also. So if the magnitude of imposed load acting on the floor is more than 3 kilonewton per meter square, okay, then 50% of the applied load is to be considered. Okay, so we have to consider 50% only for a seismic load calculation. Okay, so here as we have been given 5, so we have to take 50%, which is basically 2.5 kilonewton per meter square. So therefore 2.5 kilonewton per meter square load is to be considered in the seismic weight calculation. Okay, so that is B 2.5 kilonewton per meter square is the correct answer. Fourth question: the first, second, and third story of a G plus 3 storied building have lateral stiffness as K1, K2, and K3 respectively. As per IS 1893 Part 1 2002, the second story can be considered as a soft story if it satisfies the relation A K2 is less than 0.5 K3, B K2 is less than 0.7 K3, C K2 is less than 0.8 K1, or D K2 is less than 0.5 K1. Okay, so what is the correct this one definition of a soft story? Okay, so this subscript basically refers to the floor. Okay, so K2 means second floor, this one second floor lateral stiffness, and yeah, it has been mentioned. So 3 is the third story stiffness. Okay, so which is the correct option as per the which is the correct definition for soft story as per IS 1893 part 1 2002. Okay, so if you see in page 10 of IS 1893 part 1 2002, that is clause 4.20, you will see that there is written that soft story is one in which the lateral stiffness is less than 70% of that in the story above, okay, or less than 80% of the average lateral stiffness of the 3 stories above. Okay, so soft story will be one in which the lateral stiffness is less than 70% or zero point 0.7 of the higher above story, or it is less than zero point 0.8 or 80% of three higher average of 3 higher stories. Okay, so here I think, yeah, average is not given. Okay, so here only one story is given, so we have to consider this value 70%. Okay, so it is soft story is one in which the lateral stiffness is less than 70% of that in the story above. Okay, so that means K2 should be less than 0.7 of K3. Okay, so this, okay, B. Okay, so B is the correct option. So as you can see, B, K2 is less than 0.7, K3 is the correct option. Fifth question. As per IS 1893 Part 1 2002, story drift can be defined as A. Displacement of the top floor of a building relative to the ground floor due to seismic force. B. Displacement of the whole building relative to the ground floor due to seismic force. C. Displacement of the top floor of a building relative to the first floor due to seismic force. D. Displacement of one story of a building relative to the stories above and below it due to seismic force. So which is the correct definition of story drift? Is it A, B, C, or D? Okay. So as per IS 1893 Part 1 2002, story drift can be defined as displacement of one story of a building relative to the stories above and below. Okay, and that is basically due to the seismic force. So that is option D. Okay, displacement of one story of a building relative to the stories above and below it due to seismic force can be defined as a story drift. Okay, so D. Okay, so D, displacement of one story of a building relative to the stories above and below it due to seismic force is the correct option. Okay. Sixth question. A G plus 2 storied building is located in an earthquake zone 4 area. For this building, if the importance factor I, response reduction factor R, and average acceleration coefficient SA by G are 1.0, 3.0, and 2.0 respectively, the calculated base shear is 120 kilonewton. What will be the base shear value if the importance factor is 1.5? Okay. A 100 kilonewton, B 140 kilonewton, C 180 kilonewton, or D 220 kilonewton. Okay, which will be the correct option of the base shear value. Now, if you see here, so here calculated base shear is 120 for importance factor of 1. Okay, so if the importance factor is more, if it is increased by 1.5, so you have to also increase the calculated base shear to value by 1.5, because you know that your that value, if you see that equation, okay, that equation of your base shear, okay, so that is how that was how what that was equal to alpha into W. Okay, so alpha is Z by 2 into I by R into SA by G into W. Okay, so if you see there, you will see that you know uh, this one, if you take every like apart from the I value, if you consider every value as constant, okay, so that means your this your VB value will be directly proportional, okay, to the I value. Okay, so V value will be directly proportional to I value if you consider all the values to be your this one all the values to be constant. So that means its proportion, that is V2 by I2, will be constant. Okay, so that proportion will be constant, ratio will be constant, that is V2 by I2 equal to V1 by I1. Okay, or V by V1, V2 by V1 equal to I2 by I1. Okay, So that using that, okay, so using that we can using that value we can using that relation we can find a base share. Okay, so that will be nothing but it will be 120 into 1.5 by 1. Okay, so that is basically the this one criteria, and therefore base share will be equal to 180 kilonewton. So as you can see, C 180 kilonewton will be the correct option. So C 180 kilonewton is the correct option. Seventh question. A G plus 2 storied building having floor to floor height as 3 meter is subjected to floor load, including live load as 600 kilonewton, and it is located in seismic zone 5. For this building, if the importance factor I, response reduction factor R, and average acceleration factor coefficient SA by G are 1.5, 3, and 2 respectively, what would be the seismic coefficient? A 0.1, B 0.18, C 0.30, or D 0.35? So we need to find out the seismic coefficient. Okay, so that is alpha value, that is Z by 2 into I by R into SA by G. Okay, so I value is 1.5, R value is 3, SA by G is 2. Okay, and yeah, so we only need the Z value. So Z value is for seismic zone 5 it will be 0.36, for 2 it is zero point 0.1, for 3 it is 0.24, for 4 it is 0.3, and for 5 it is 0.36. Okay, so it will be 0.36 by 2 into 1.5 by 3 into 2. So this, okay. So Z is 0.36, I is 1.5, SA by Z is 2, R is 3. Okay. So seismic coefficient H is Z by 2 into I by R into SA by G, that is 0.36 by 2 into 1.5 by 3 into 2, that is 0.18. So B 0.18 will be the correct option. Okay. Eighth question. A G plus 2 storied building having floor to floor height as 3 meter is subjected to total floor load including live load seismic weight as 800 kilonewton, and it is located in seismic zone 5. For this building, if the importance factor I, response reduction factor R, and average acceleration coefficient SA by G are 1.5, 3, and 2 respectively, what would be the magnitude of base shear force that need to be considered in the design of the building? A 192 kilonewton, B 177 kilonewton, C 164 kilonewton, or D 144 kilonewton. So if you see this question, so this is just the similar, this is the same question as with regards to the last question. Only we have to find the base shear force. Okay. Here they ask to calculate the seismic coefficient. Now we have to calculate the base shear force. So seismic coefficient, as we found, it is how much? 0.18. So here also, if you see this 0.18, and we have to find base shear. So for that, we have to just multiply 0.18 with the total load. So total load subjected to total floor load including live load as seismic weight as 800 kilonewton. So we have to multiply 0.18 with 800. Okay. So if you multiply 0.18 with 800, it is how much? It is 144 kilonewton. Okay. So that is D. So option D, 144 kilonewton is the right option. Ninth question. A G plus 3 story building having floor to floor height as 3.2 meter is subjected to base shear force of magnitude 250 kilonewton, and its each floor is subjected to floor load of magnitude 600 kilonewton. What would be the lateral seismic load acting at the second floor level of the building? Okay. So A 20.67 kilonewton, B 26.67 kilonewton, C 30.77 kilonewton, D 33.33 kilonewton. A, B. So which will be the correct option? A, B, C, or D. Okay. So we need to find the lateral seismic load acting in the second floor of the building. Okay. So if you remember, the formula is WI square by summation of WI square into VB. Okay. So VB here is 250. Okay. And yeah, so each floor is having a load of to 600. Okay? So yeah, so let us see how to calculate. So each is 3.2, each floor is having W weight 600. So you have to calculate the WIHI square value for each floor. Okay. So yeah, so if you see, height is 3.2 meter for every floor and weight is also 600 for every floor. So W1 H1 square is 6144. Okay. W2 H2 square will be 24567. Okay. So if you see here, the W value always stays constant, but the height, okay, height will increase from like height is not the story height. Okay. So this height is height of your considered floor from the base, from the ground. Okay, so for the first floor, the height will be equal to the story height. Okay, but for the second floor, the height will be equal to two times the story height. Okay, similarly for third floor it will be three times, and for fourth floor it will be four times. Okay, so you get the WIHI square value for first floor is 6144, for second floor is 2456 for 576, third floor is 55296, and fourth floor is 98304 kilonewton meter square. So total summation WIHI square will be 184320, 1,84,320 kilonewton meter square. And base shear VB is given already, it is 250 kilonewton. Okay, so therefore lateral seismic load acting at the second floor level will be this value, 24576 divided by 184320, okay, into 250. Okay, so yeah, it has been written here. So lateral seismic load acting at the second floor level will be Q2 equal to VB into W2H2 square by summation J equal to 1 to 4 WJ square. So it is 250 into 24576 by 184320, that is equal to 33.33 kilonewton. So as you can see, D, 33.33 kilonewton is the right option. Okay. Last question. 10. A G plus 3 storied building having floor to floor height as 3.2 meter is subjected to base shear force of magnitude 250 kilonewton, and its floor is subjected to floor load of magnitude 600 kilonewton. What would be the lateral seismic load acting at the third floor level of the building? Okay. A 50 kilonewton, B 75 kilonewton, say 90 kilonewton, D 100 kilonewton, which is the correct option. So basically it is the same as last question, only difference is instead of second floor we have to find at the third floor. Okay, what is the lateral seismic load acting? So therefore it will be nothing but it will be equal to 250 into 55296 by 184320. Okay, so just you have to replace 24576 with 55296. So as you can see, I think, yeah, so as you can see, this is only what they have done. So they have just replaced, actually this should be W3, okay, not W2. So they have just yeah, so they have just replaced your W2 with yeah, they have just replaced the second floor with third floor. So this should be third floor. Okay, it has been mistakenly provided as a second. So it will be 250 into 55296 by 184320. Okay, so that is what, so it comes out to be 75 kilonewton. So as you can see, B, option B, 75 kilonewton is the correct option. Okay, so yeah, so with this we come to the end of this course. Okay, as well as the discussion. So I hope that you have at least learned something out of this course. Okay, and you have at least learned the basics of how to design. Okay, the basic elements, structural elements of reinforced concrete. Okay, that is a beam, column, slab. Okay, staircases, footings, etc. So I hope that like with this hope, like that you will be able to apply this. Okay, and solve some practical problems. Okay, so I hope that you will be able to do this. So yeah, so with this I would like to end today's discussion. So good night, and wish you a great future ahead. Okay, yeah, yeah, thank you. अच्छा मतलब आप बता दीजिए, मैं देख के बताऊंगा, है ना? ओके, मतलब वो किसका किसका क्वेश्चन था, मतलब मतलब did I solve it or it was given in the assignment? Like मेरे लिए तो class today is the end. Okay, like I don't know about whether the course instructor is organizing any extra classes, so for that you have to ask Dhang sir. Okay, so हाँ, okay, कोई इशू नहीं है, मतलब you can do one thing, like you can आप आराम से, मतलब you have time, right? Okay. Okay. Yeah, matlab, there must be some typo mistakes, okay? So you have to self correct that, okay? Because it is such a long course, okay? So people don't have time to see every each and every word in sentence, okay? So I apologize for on behalf of them also, but please try to self correct them, okay? Ultimately the idea is to make you understand, okay, how it is applied, okay? So if you are able to do that, so it is very nice, okay? So yes, yeah, Venkatesan, I think you will be allowed to take the code book, okay? But it is better you ask sir, okay, Dhang sir, for confirmation, because I will not be the correct person to answer, but it should be allowed. And I think they will give you the main values, okay? Yeah, yeah, yeah. Because those values will be requiring, right? For for putting for finding values, right? So I think yeah, so you can take this, and also I think they will mention give the required values, like all those important values. Yeah. Huh. Huh, right. So they will provide. Yeah. So I don't think you have to, you don't have to be afraid of those things. Okay. So they will make it available. And अगर कुछ ऐसा होता भी है ना, you just inform the this one authorities. Okay. So you will, they will cut that question and give you all some grace marks, okay? So I don't think that is a issue. So okay then, good night.